Hello everyone, I'm André Schumacher, and today I want to introduce you to the attack known as SQL injection. But first, a few words about myself. I'm a student of applied informatics, currently in 6th semester. Before taking up studies, I finished a vocational training as an IT specialist for application development with a software house specialized in custom web applications and e-commerce. It's during that time that I've had some hands-on experience with the topic of today's presentation. Every developer intending to program for the web should be aware of SQL injection, as it is by no means a thing of the past. Recent occurrences should showcase the prevalence and scope of this attack. Amongst those are names like the widely used Drupal CMS, IoT cameras of German manufacturer Göteborg, and the enterprise-grade e-commerce platform Magento. In the following 20 minutes, I will run you through the technical fundamentals necessary to understand this attack, followed by a detailed account of its workings, and finishing up with the common practice developers employ to avoid falling victim. And as the saying goes, seeing is believing. You will be provided with a step-by-step demonstration of the attack and where it stems from, as well as the countermeasures. But before we get into that, first some basics. The name SQL injection refers to injecting a malicious database query into an application, which is then passed to and executed in the database connected to said application, resulting in consequences a developer would like to avoid, such as unauthorized access or loss of data. Think of it like injecting a substance into the bloodstream which is transferred to the brain, where it causes potentially harmful effects. Typical targets for this attack are web applications, as those tend to be open for everyone to access and commonly store persistent data in one database. In case of an online shop, that could mean credit card information of potentially thousands of customers. From this myriad of users, it only takes one with malicious intent to wreak havoc in the system. From a technical perspective, SQL injection is a comparatively simple attack. In contrast with more sophisticated hardware-oriented exploits, where ingress requires deep levels of understanding, substantial preparation, and meticulous execution, SQL injection is more akin to casually strolling through an open door. One only needs to find it. In short, basic skills in querying a database is all that is required. The reward can be enormous, and the pool of potential attackers is sheer endless. Now, how would you go about injecting some SQL where it's not intended to go? As mentioned before, the hardest part is just finding the door. In this case, it often comes in the form of a simple HTML input field with the purpose of taking user input, running that through a database and possibly returning the results. Think of search bar, input field, or login forms. Those take your input, and upon submitting the form, it is sent to the server where your data will be processed. In most cases, the receiving code will contain a prepared SQL query with placeholders to be filled with your input. The resulting complete query is then sent to the database for execution. Now, let's assume the developer did not follow proper coding standards and left the application open for attacks. In this case, it means that the code uses basic string concatenation to get your input into the prepared query. Armed with that insight and your knowledge about SQL, you can craft your input in a way that alters the workings of that query. If the server-sided code fails to handle your input with proper care, the database will execute your malicious query without question. Building this type of input string usually involves any text that would normally be expected here, followed by a single quotation mark. This one acts as a closing counterpart to the opening one in the prepared query, just before the concatenation of your input. If you plan on making use of the intended query, the input could then contain, for example, additional conditions for a where clause that always evaluate to true. Note the missing single quote at the end, as this will be added by the example above, just before the semicolon. If you intend to substitute a different query, the next part of your input after the intended part would be a semicolon, which marks the end of a query. From there on, the input can contain any kind of SQL query, which will be executed as well as a separate query to the one that was just closed by the semicolon. The end of the input should contain a double dash or pound sign. Depending on the database installation in use, those are characters denoting comments within the query, not to be executed by the database. Here it serves the purpose of disabling any attempted execution of the remaining parts of the prepared query following the input. To showcase this attack, let me give you a quick demonstration. Now, to showcase SQL injection in action, here we have a mock-up of very basic login screen, usual username, password. If we are typing in just any random logins, everything here in plain text for demonstration purposes, but with any random input, we will not get access to the system. But now, with our knowledge about SQL injection, there are ways around that. So, as before, we are finishing up the intended input, finishing the single quotes, and then adding an additional where clause that always evaluates to true. And again, we are leaving out the closing single quotation mark. And now with this input, suddenly we have access to the system. As you can see here, now we have entered as the admin account. The reason for this is the admin is the first entry in the database in the user table. And since our query returns true for every single entry, the first one will let us in that case, the admin. In here, to demonstrate, it's a simple mock-up of a product search with a handful of sample products that could be found, for example, in an online shop. As we can see here, we have 3 products with name, description, and so on. Now in this search field, we can filter this list below. Let's say we are searching for something that is called product. As you can see, some of those have product in the name, but not all. And as expected, the list is now filtered. From that we can infer that the underlying query for this input field here utilizes a like condition, meaning the search term doesn't have to exactly match, just partially, to return the result. Now, to forge from that some SQL injection input, as mentioned earlier, we have to finish the regular input with just about anything. But because it is a like condition right now, which is utilizing the percentage sign, this we have to close as well, just like the single quotation marks. And here we can finish up the underlying query with the semicolon, and from here just add any additional new query. Let's say we want to see everything that is in the users table. Well, here again we are finishing with the semicolon but ending with the pound sign, because in this my local MariaDB installation the pound sign denotes the comment character, which means that any following parts of the underlying query will not be executed. Other installations might use the double dash, this one uses the pound. And with that, suddenly instead of the products, we are seeing the entries of the user table. Over here we can see that we have 3 users in the database. Some of which already are admins, some should not be. To get into detail about how the underlying structure works, let's have a look at the code. For that, first let's see the login page. We are simply taking the user input from this form's post, meaning the username and the password, and passing that along to a validate login, in this case unsafe function of a model class. So let's have a look at that. This one, as mentioned before, uses very basic string concatenation, a prepared query part, to which it simply adds the passed username and then adds the password. And then, without any further question, simply queries the database with whatever we put in here. If any rows are returned, meaning our conditions match, will be redirected to the proper inside of the system. Otherwise, we will get an invalid login. As was demonstrated earlier, with a very simple crafting of the passwords input in here, we can bypass any checks, any entries of the user table will return, and therefore we will gaining entrance. After entering the system, we would see the results of this site. Simple search field plus the output of the results that we might get from the product's search. In this case, again, of the unsafe variant. Let's have a look at that. And again, we are simply taking the input that the user put into the search field, not asking what is in there, only if it is empty, and from there simply adding it to our prepared queries. From there on, the variants of those sample products are added. The reason for this is it should showcase some use case of, in this case, the multi-query functionality, where it might be useful. So now, in this questionable piece of code, the products query and the variant query will be just concatenated again and as one sent to the database. Those will return separate results, which we are now gathering, a bit of forming together and sending it to the front. Now, with some simple changes on the login, let's make it a safe variant. So we are logging out. Again, trying our random logins, and it is not working. Just as now, our crafted SQL injection does not function anymore. Only option to get access to the system now is with proper logins. The reason for that can be very easily verified in now the different function in the code. In this one, just as in the first one, we are receiving the username and the password. But as a difference to this first one, we are not using simple concatenation, but rather we are preparing a statement that utilizes specific placeholders. From there on, we are utilizing a function of the MySQL I library, note the I, as this one offers prepared statement. So we are preparing a statement from our query. That would be this one. And now to this statement we would have to bind the parameters. Therefore, we are using the Statments function to bind parameters, which would be two strings. That's why we are writing two S's here. One string for the first question mark, one string for the second question mark. And then following that with the appropriate amount of string inputs. The difference to the demonstrated unsafe variant from before, where it simply queries the database, is that in this case the bind param method provides some internal escaping, filtering, and basically sanitizing the input. Meaning with our crafted SQL injection, what we entered into the password field, this bind params will not work. From here, this execute will then also not result in any output, as this, without any parameters put in there, is not a valid query that might give us any results. Therefore, with those simple changes compared to this method, our login is now safe. But now that's not all which you can do with, for example, some different SQL injections. To showcase those, let's log in again. As we might remember from those outputs before, we have some login, seeing the same mask again. But now, instead of using the unsafe get products method, we are using the one without variance. Let me quickly show you the differences. The products unsafe method, in addition, queries a different table that holds variations of all products, while this one provides only the base products. This comes in handy for demonstrations, as the further queries such as this product variations hinder to some degree the further demonstrations. So now let's get back here, have a look. We only have those three base products. But remember, we are still using the unsafe method. So here, this one is still open to SQL injection. For example, we can select everything from the user table once we have properly closed up the original prepared query. Submitting that. Again, we are seeing all users. But now, instead of that, let's say we want to see what else the database has to offer with show tables. Now we can see, in addition to users and products, we have the before mentioned variations, we have a separate copy of products, and we have customers. So let's say we want to cause some damage in the database. So instead of just letting us see all the tables, let's say we are dropping some tables. For example, the products table. As expected, no output. But now, if we are searching searching for specific products, nothing will be returned, as the entire inventory of the job is now deleted. So let's recap those countermeasures. Input to your system from the outside needs to be properly sanitized. Simply escaping certain characters is a start, but not enough. You should also not attempt to build your own sanitation functions, as it is prone to error or oversight and also unnecessary. The better alternative to that is to use tried and true libraries that offer prepared statements. Thankfully, those are available as part of the database connector libraries of all major languages. They are as easy to use as they are robust, so you'd be well advised to utilize them. In conclusion, I will leave you with what can be considered the first rule of software development. All input is evil until proven otherwise. And with that, I hope you've learned something today, and I thank you for your time and attention.